Hi everyone, how are you doing? So let's get started. Hello Satyam. So we were discussing few questions on stack and queue, and I think few questions were remaining. So let's just see few remaining questions that we are yet to see, right? Okay. So let's see this question number 16. What does this say? That suppose you have a stack, and that stack is containing n elements. Now they are saying describe in English. Just a second. Let me connect. Okay. So they are saying that describe in English how you can scan S to see if it contains a certain element small x, right? So you are allowed to use one additional stack or a queue. So I hope you understood the question. The question is that you are having one stack and you want to check. Let's suppose there are some element 2, 1, 3, 10, 7, something like this, right? And now you want to check whether some element, let's suppose element 3 is there in this stack or not. Okay, this is the question. Please note that you must preserve the original order of the elements in the stack, and you are only allowed to perform push and pop operation on the stack, right? So which means that you need to return whether this 3 exists in this stack or not, and also you are not allowed to change the element of the stack, obviously, right? Neither the order of the elements nor any element you can change in the stack. So what can you do? How you can check whether 3 exist or not? So since it is a stack and we can only look at the top, so we will be looking at the top, and if we will be checking whether, okay, so my question is that is 3 in a stack. So what you will be doing, you will be checking whether top of the element is 3 or not. Since it is not 3, what you will do, you need to check the next element, but you cannot directly check the next element. You have to pop this element. So what you will be doing, you will be saying that, okay, let me pop out this, and then now you put this element, let's suppose in a queue. I will tell you that why we are putting in the queue or in the stack, where you need to put. Let's just check. Okay, so I think you need to put in the stack, right? Okay, let's just see. So so suppose that you put in the queue or in the stack, we will see that which one is more appropriate. So suppose you do one of this. So this is one extra stack that you are taking. Okay, extra stack. So you pop this out, and then you check whether 10 is 3 or not. Since it is not 3, you will be putting the either in the stack or in the queue. We will check like which one is more relevant. Then you will checking that, okay, 3 is there. So then you will be returning that, okay, I mean 3 is there. So now you have this original stack which is having 2, 1, 3, right? Now you need to again put 10 and 7. So I think it is better to use this extra stack because it will be giving 10 and 7 in that order. I mean, such that the 7 is on the top. Okay. If you put in the queue, then what will happen? Then it will be giving 7 first. But you don't want 7 first, right? You want 10 first. See, what is the case? What is the case? You are basically having this. You are having 2, 1, 3, right? In the original stack because you have popped these elements. And then you are saying that, okay, 3 is there in the stack, then you are returning true. But before you return true, you must preserve the original stack. So in order to preserve the original stack, what you can do, you can basically you have to basically put the remaining elements here, which is 10 and 7. So first you need to put 10 and then you need to put 7. How you can achieve this? You must be using one extra stack, right? If you're using queue, then 7 will be first popped out, or the dequeued element will be 7. Then you don't need 7 first, you need 10 first. So that's why this is preferred, right? So you can do 10 and 7, and then you will be returning true. Okay, so basically what you can do, we can use queue to process the element in 2 phases. Okay, they are using queue. Let's just see how they are using queue. In the first phase, we iteratively pop each element from S and NQ to Q, then iteratively DQ each element from the Q and put it to S. This reverse the element in Q. Then we repeat this same process. Okay, we don't need it, right? I mean, you can do it. So basically what they are saying that you need to pop out all the elements, whether you, I mean, 3 exist or not. You cannot stop. You need to pop out all the elements. So the strategy that they are suggesting is something like this. If you're using a queue, then they are suggesting something like this, that 2, 1, 3, 7, 10. Let's suppose this is the stack that you have. You want to check whether 3 is there or not. Okay, you can check 3 is there or not, but you have to pop all the elements and put in the queue. So first you put 10, then you put 7, then you put 3, and then you will say that okay, 3 is there, but don't you can stop your checking, but don't stop this procedure, right? 1 and then 2. So this is the extra queue that you are using, right? And this is your original stack. Now original stack is empty, and then you have this situation in your hand, which is this is the empty stack, right? What you want to be you want this 2 at the bottom of the stack. So what they are suggesting is that you have this scenario, right? Now what you can do, you can dequeue, or you can pop this 10 and then you can put in the stack, but there is a problem. Can you see the problem? See, this is the current state. Have everyone understood how we are reaching to the current state? We are popping out all the elements, putting here, right? Now, if you are dequeuing this 10 and then putting here, and then dequeuing this 7 and then putting here, which means like after this state, if you are doing something like this, okay, you dequeue this, put this, you dequeue this element, put this 3, 1, and 2. Then the order is reversed, right? The order is reversed. And then we have this as the current state, which means we are having Q as empty. I mean, Q will be empty in that case, obviously. So we are having empty Q, right? I mean, this Q will be emptied and stack will be full, right? So this Q will be empty, and then you are having this. But what you want this 2 to be or the bottom, right? This is empty Q. So now they are saying that you do it one more time. I mean, you put this 2 here, which means you will be saying that okay, now this 2 is here, and then 1, 3, 7, 10, right? And now you do it. I mean, you again dequeue and then push in the stack, right? So now you have the empty stack. So basically, currently you are having the empty stack. And then what you can do after this state, you dequeue the element, put it here, 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 dequeue the element, put it here. So basically, finally, you will be having 2, 1, 3, 2. I mean, from the bottom 2, 1, 3, 7, 10. Finally, you will be having this, but it is too long, I think, right? I mean, you can do this, but it is too long. So basically, if you're using stack and queue combination, one thing you observe that the thing that to be observed here is that we are basically reversing the element, right? I mean, suppose if you put all the elements from this stack, okay, to this empty queue. Let's suppose this is the empty queue, and this is the stack which is having some elements. Okay, suppose these elements are A, B, C, D. Now, if you are performing this operation, which is basically putting all this here and then putting all this here, then can you tell me the final state? After that, what will happen? You will be again having empty queue, right? You will be again having empty queue, but this time the stack order elements will be reversed, isn't it? Yes. So this will be reversed. Now it will be DCBA, right? It will be DCBA. I mean, from the bottom, it will be DCBA. So one thing you have observed is that if you are basically doing this, I mean, if you are just putting all the elements and then putting back, then what it is doing, it is reversing all the elements in the stack. But this is, let's suppose, is not desired thing. Then what you can do? You can do this one more time, isn't it? I mean, if you do this one more time, then what will happen? After this, you will be having, I mean, one stack, one queue, which is again empty, but this is ABCD this time, right? So basically, if you're doing one time this, it is reversing the elements of the stack that you can easily observe, right? So they are suggesting this technique, but that is okay. I mean, you can also use one stack. That is, I think, better. Okay. Cool. Now let's just see this question. In this problem, we consider two stack A and B manipulated using the following operations. N denotes the size of A and M denotes the size of B, which means you are having A and this size is N. You are having another stack B and this size is small m. Now they are saying this push A means you are pushing to the A, push B means you're pushing to the B, and then transfer K means they're repeatedly popping the element from A and pushing it to B. So if you're transferring, then it means transfer K means you are until K elements have been moved or the K, A is empty. So basically transfer K means you are transferring K elements, right, from here to here. Is this clear to everyone? You're transferring K elements from here to here. Now they're saying that assume that A and B are implemented using doubly linked lists such that push A and push B as well as single pop from A or B can be performed in order one. Okay. I mean, you can perform any of this operation in order one in worst case. Then what is the tightest bound on the worst case running time operation of this transfer? So how many elements you can transfer in the worst case? N elements, right? All of these N elements you can transfer because this size is N. So what is the tightest bound? Will this depend on this M? I don't think, right? So it is easy question in the sense that you can say the tightest bound will be N. I mean, this you can say, in fact, theta of N. Okay. In worst case, it will go till N. In worst case, it will go till N. So you can say theta of N. It will not depend on M. Okay. It will not depend on M. These operations, these options are wrong. Because I don't have anything to do with M. I'm transferring all the elements from here. In the worst case, I can transfer all these N elements. So that is why it is theta of N or order of M. Okay. But it takes order of one complexity for any operation because you're transferring N elements. No? Transfer case bulk transfer. You're transferring N elements. In the worst case, you can transfer N elements. So since for every element you are taking order of one, but for N elements, you will be taking N or order of N, right? Because you are doing bulk transfer. Okay. Now let's move to the next question. Let's see this question. Given a stack which is having 15 elements and a queue which is having 30 elements. Okay. So they are saying that you are having a stack which is having 15 elements. And this is a stack. And there is a queue which is having, I think 30 elements. Okay. And this is a queue. Okay. Now they are doing performing the following set of operations 60 times. They are doing this operation 60 times. And what are the operations which are given to me? They are saying that you are enqueuing, I mean the popped out element you are enqueuing and you are doing this 60 times. Okay. So you want to perform these operations 60 times. Now, what they're asking is that how many of these 45 elements are involved in this process? This is not asking how many times element move, but how many are okay. So basically, how many of the elements you are basically touching? Touching means like you are involving. Okay, let's just see. So suppose these 15 elements could look like this. Maybe let's suppose 1, 2, 3, 4, 15. Okay. Suppose these are the 15 elements that I have. And let's suppose here also I have 16, 17. I have 30 elements, right? So it will go 17, 18, I think till 45. Okay. So suppose these are the elements. Now what I'm doing, okay, let's just check what I'm doing. I'm popping out one element from here. Okay, this is just one time. Let me just see what I'm doing one time. Then we will see that how to do it 60 times, right? We are doing it 60 times. Ultimately, we are doing 60 times. So let's just see how we are doing one time. We are popping out one element from here, enqueuing to the queue, okay, and then dequeuing from the queue, pushing out the dequeued element, right? Okay. So basically, after one time, my stack and queue will look like this, right? So this 16 has been moved here. This one has been moved here. Okay. So this is after one time. Let's suppose iteration, I'm saying it is k equal to 1. I mean, after one iteration. Okay. Let's see after two iterations, what's going to happen. Now, I will pop out this, push, I mean, NQ this here, DQ. I will, I will DQ this. I will push it here, right? 70. This is after k equal to 2. Is this understood to everyone? That initially I was having this, then I need to pop out one element from here, push it here, and I mean I need to do something like this. I need to put this one here. Top of the element should go on this queue, and this dequeued element should go to the top of the element, right? So that's what I'm doing. So basically, this is the initial step. Now, now basically this one should go this top, this 16 should go here. Okay. Now 16 should go, I think, on this top, and then 17 should go here. Now 17 should go on this top, and 18 will go here, right? So maybe I can write it. Okay. So now basically let me write it in this way. Okay. I mean, this one was on the top, then 16, and then you will be having 17. So 17 will go on top of this. I mean, we will be writing it in the queue. So maybe let me write in the queue. Okay. So 17 will go here, and instead of 17, you will be writing 18. This is after k equal to 3. So you're not even touching this 2, right? That's what I was just observing. You're not even touching this 2. So whatever you are doing, I think you're involving just one stack element and some of the queue element, right? Now, since these elements are 30, so I think you will be touching all of this, right? You will be touching all of this because these elements are 30, and if you do it 30 times, I mean, you are actually doing it 60 times, right? You are doing it 60 times. If you do it 30 times, then only I think 30 times or 35 times or 31 times, something like that, then I think you will be at least touching all of these elements. And you are never touching this 2. I mean, there is never a case that you need to touch this 2, right? So you are touching all of these 30 elements, and also you are touching this one. So that's why you will be touching 31 elements, right? You are touching 31 elements. Is this okay to everyone? That you will be definitely touching all of these because you are doing 30 times. I mean, sorry, 60 times. Then you will be definitely, I mean, you keep on touching 19, 20, and then eventually it will be 45. Then again, you will be doing something like that, right? But you are never going to touch this 2. Reason being is that we have to touch this one because that is the starting point. I mean, you have to cross this off, and then you will be basically putting it there, right? But now we are always playing on the top of the stack. I mean, we never need to go beyond the top. Are you basically popping 2 elements incrementally? I mean, one after another subsequently? Are you doing 2 pops subsequently? No. You are doing a pop, and immediately you are putting something in that particular vacant location, right? In the top of the stack. So basically, you are always going to replace this top with something. You are never going to touch this 2. You can only touch this 2 whenever you are having 2 pop operation contiguously. But you are having a pop operation, and immediately in the stack, with respect to stack, you are pushing something, right? So pop and then push. So that is the reason you are never going to touch this 2. Is this understood to everyone? I mean, you are only playing with these elements. You are putting something here, then doing something like that. If you are doing it 60 times, you will be touching all of these elements. That is for sure. But you are touching this one also. That is why total elements that you are touching is 31. Okay. Let me know if there is any doubt here. So the answer here is 31. Okay. Let me move further. I hope that is fine. Let me know if you are still in doubt. Anyone is still in doubt? What does remove last element from queue means? This is not the last element. This is the, this is the first element, right? I mean, in the queue, you dequeue from the from one end, and then you enqueue from another end. Queue works differently from the stack. In stack, you do all of this in from the one end, but in the queue, you dequeue from one end and you enqueue from another end, right? So you will be dequeuing from here, and then if you need to enqueue, you will be enqueuing on the top. Remove the last element of the queue. This is their terminology. Don't worry about this terminology. Okay, this is their terminology of the DQ, whatever they are saying, first or last. I mean, this is their notion. This is just a normal DQ. Okay, I mean, you can just consider this. Okay, let's see this question. I think this question was very interesting, right? Okay, how many of you solved it? Okay. So Rishesh is saying he has solved it. So Rishesh, what was the answer that you are getting here? Can you write the answer for both part A and B? Let's just see what this question is saying. So this question is, one of the simplified version that was originally present. So I just posed the push operation. Okay, I mean, you can do push and pop both, but I'm just asking for the push operation. So let's just see what this question is saying. So let me tell you what this question is saying. I mean, the simplified of what was already there. Okay. So see, they are saying that you need to implement a stack. Okay. You need to implement a stack. Let's suppose this is a stack in such a way that inside this stack itself, there are multiple stacks. Okay. So there are multiple stacks inside this stack itself. So which means that there are, let's suppose these many stacks that you are having. Okay. Which means that yeah, that is basically they are calling multi-stack. Okay, so they are saying that there is a combination of multi-stack, or I think that's what they have used, right? A multi-stack consists of infinite series of the stack where the ith stack can hold up to 3 power I elements. Okay, so suppose this is the stack that we had earlier. Okay, I mean, to start with. Okay. So suppose, I mean, such that, I mean, there are multiple stacks, okay? And every stack is having 3 power I elements. So this is having 3 power 0 elements. I mean, this can hold 3 power 0 elements. This can hold 3 power 1 element. This can hold 3 power 2 elements. This can hold 3 power 3 elements. This is the case that is given to us. Is this okay? At least what is given? Okay. The sizes of the stack. Now they are saying that suppose if you want to push any element, then what you can do, you can push any element in the first stack only, which means even though this stack is empty, you cannot push any element here directly. Okay, suppose here 5 elements are there, okay, or maybe let's suppose 9 elements are there or something like that, right? Then can you push any stack directly? See, here any element directly. See here 27 elements can come, but suppose still I mean, 27 is its capacity, but still you cannot, still if even if it is empty, you cannot push any element directly here. What you have to do, you have to push any element in this stack 0 or stack 1, whatever you want to call, in the first stack only. Okay. So you only have to put the element, I mean, the push operation will only have to do in this first stack. Now, what if this first stack is full? Then what you will do? You will move all the elements from here to here. Okay. And what if this stack is also full? You will move all the elements from here to here and so on, right? So basically, let me just show you one operation. Okay. Suppose I'm pushing one element here. Okay. Suppose there is one element that I'm pushing. Now, once I push one element, I have to push in the stack, first stack. Is this fine to everyone that we are pushing this element in the first stack? This is the first push. Now, suppose I want to push one more element. Okay, I want to have push operation here. then what will I do? Can anyone tell me? I will be checking. Sorry. So I will be checking if I have to push any element here, I will be checking whether this stack is full or not. If this is full, then I cannot push this directly. I have to first move this element, right? I have to first move this element from here to here. So I need to move it. And once I move it, then only I can push it, right? So let me just move it. Okay. So basically, I was having this situation. I can push one element, but for the next element, since this was already occupied and I can push in this only, then I have to move this element from here to here. That is I just done, and now I can push it, right? Now I can push it. Is this fine to everyone? Okay. Now, I mean, this is what it is given here, right? Cool. Now let's suppose, now these are the two elements that I have pushed till now. Now let's suppose I need to push one more, okay? Now what you will do? Again you will say that there are, I mean, here, there are, this stack is already full. Yeah, this stack is already full. You have to push this element here, and then only you can, I mean, you need to move this element to the next stack, and then only you can push, right? Okay. So, just a second. Let me copy this so that everything is clear very visually that what I'm doing, right? Okay. So if you need to push one more element, you first have to move this element from here to here. And then you can push one more element here, right? So this is how the three elements I'm pushing. Okay. Is the scenario clear to everyone that what they are doing? I think this is fine, right? So if you have to push, let's suppose this is the current scenario. If you have to push one element, you have to basically move all of these elements, right? And then all of these elements, then all of these elements, and then you have to push. So this is what it is given. Okay, cool. Now, now they are asking two questions. Let's just see the first question. State the worst case time complexity to push one element onto this multi-stack elements, right? Containing n elements. Okay. So they are saying, suppose this is already containing n elements, then how much time complexity it will be taking to push one more element? Okay, just think about it. This is the total stack. I mean, to outside word, this is the stack. Okay, you don't even know that there are multiple stacks here. I mean, this is called multi-stack, but I mean, this is just a stack A. Okay, let's just call it stack A or stack, I mean, whatever you want to call, okay? Stack, my stack. Okay, let's just call it my stack or multi-stack, whatever. But this is one stack. To outside word, there are no multiple stacks inside. If I'm saying, if someone is saying what is the worst case time complexity to push one element, if the stack is already containing n elements, which means this stack is containing. Now, this n elements could be distributed anyhow. Okay. Now, these n elements could be like one element could be here, 5 elements could be here, 10 elements could be here, and I don't care about it. Okay. The n elements could be distributed anyhow, but I'm saying that you are already having n elements. Now, what could be the worst case time complexity to push one more element? This is the question. Is the question clear? Combinedly, all of these stacks are having n elements. See, they are saying that state the worst case time complexity to push one more element onto the multi-stack, right? I mean, this is the name of the stack, containing n elements. Multi-stack containing n elements is what? That the stack name is multi-stack or my stack, whatever you want to say. It is containing n elements, right? Now, they are saying if you want to push one more, okay, then what is the time complexity? So, in worst case, what may so happen is that, let's suppose these are the n elements, right? These are the n elements. Now, in worst case, what may so happen? that this element can do order of one work. I mean, we might have to shift this element to the next stack. See, suppose my n is such that my n, the number n that I'm talking about, is such that which is basically in some 3 power k, or I mean, not need not to be 3 power k. What I'm trying to say is that it is basically summation of all of this. Okay, I mean, let's suppose this is also full. My n is such that in the worst case that all of this is full. Okay. Now, since all of this is full, right? I hope you are getting, but let me just make another diagram to make it very clear. So let's just solve this part A. Now they are saying that what is the worst case time complexity? Let's suppose this, all of this is full. Okay, all of this is full. I mean, I don't care about the number of stacks. Whatever the number of stacks, I mean, you can easily calculate the number of stacks also. The reason being is that this is containing 3 power 0, this is containing 3 power 1, this is containing 3 power 2, this is containing 3 power 3. If let's suppose there are k stacks which are full, this is containing 3 power k. So 3 power 0 plus 3 power 1 plus 3 power 2 till 3 power k can be n. And that's how you can find out k, which is the number of stacks. But let's not worry about it. I mean, we will come to complex calculations. But first, understand this easy calculation. What I'm trying to make is that let's suppose that you are pushing one more element, and this stack is already containing n elements, and n is such that in worst case, see, worst case is in my hand, in the sense that whatever the worst scenario I can assume, I'm allowed to assume. Okay, given the algorithm, I cannot change the algorithm. What is the algorithm that you have to push here? If I can change the algorithm, then what will the change of the algorithm? Can anyone tell me that I'm pushing directly here? Then in the worst case, what will be the time complexity? Order of 1. But is this allowed as per the algorithm? No, right? So basically, as long as you are sticking to the algorithm, you can take any worst case. Okay, we will make it very clear in the algorithm subject, because that's where you need to deal with the worst case and then these things more. But I think I try to make it clear in case of linked list, in case of binary search tree. I made it an explicit video, right? And also I think in the data structure also we have the explicit heading called asymptotic analysis. No, best case, worst case. I think there are 1 or 2 videos I have explicitly made in the data structure also, to make it very clear that what is the worst case. As long as you are obeying your algorithm, whatever the algorithm is given to you, okay, you cannot change. Obviously, if your algorithm is changed, then there is no point in talking about the worst case, best case algorithm. As long as the algorithm is preserved, you can take any case, any worst that you can think of. So basically, I'm saying that let's suppose all of this, okay, these are the n elements such that all of this is full. Now, if you want to push one more element, then in the worst case, what must happen? All of this may have to move to the next stack, which is larger than this. All of this may have to move here. All of this may have to move here. All of this may have to move here. So for every n element, I mean, for every single element, I'm doing order of 1 operation, right? Because I'm moving it only once. Am I moving it twice? No, right? I just need to move all of this in the next stack, all of this in the next stack, all of this in the next step. So basically, for all of this this element, I just need to do order of 1 operation. So for n elements that are already there in my stack, I need to do order of n of work, right? This is the time complexity in the worst case for one push. Is this okay to everyone? For one push itself, this is the time complexity. So what is the answer here? Order of n. Order of n. Right? I mean, this is the worst case. But let's see this question number B, which is very interesting. Okay. Have we did it correctly? This is order of n, right? I think we did it correctly. So these are the n elements that you are having. You might have to shift all of these elements, right? Here, you might have to shift all of these elements. And that is why everyone is doing order of 1 work. Everyone is doing order of 1 work, right? This element, 1 push, 1 pop. No, why you need to shift more than once? There won't be any case. See, here, if you need to move, if you need to move, what you can do, you will never be having any chance. So basically, if you need to move, you can push all of these elements here, right? I mean, if this is empty, then there is no problem. Let me just explain you in a way. See, consider a case that this is 3 power k, let's suppose. Okay, this is 3 power k plus 1, right? I mean, basically, whatever, if it is kth number, it is 3 power k. If it is k plus 1 number, this is 3 power k plus 1, right? Okay. Now, how much larger this is? Is this twice, thrice? Can anyone tell me how much larger is the next step and next stack in terms of the first stack? 3 times, right? Yes, 3 times. So basically, I mean, the number of elements it can hold, the next stack can hold, is basically 3 times the previous stack. So if you're putting the elements here, then it, okay, let me just explain you one thing. See, tell me one thing, is that when you are moving from here to here, whenever this stack is full, I mean, obviously, right? If let's suppose this stack is not full itself, let's suppose this stack is itself empty, then do you need to put all of these elements here to here? Let me know. No, right? I mean, if this stack itself is empty, if you want to push, then you can push. I mean, ultimately what you can do, you can push here, right? If this stack is empty, then ultimately you can push here. So you will get to understand what I'm trying to make a point, is that if this stack is full, only when you are pushing, you are shifting from here to here, right? So basically what you are doing, you're always putting the elements in the power of 3, which means this stack will be containing the elements in the power of 3, which means 3 power k. I mean, if this is 3 power k, is this is, let's suppose, 3 power k, then this stack will be having 3 power k. If you're putting one more time, then one more 3 power k. If you're putting one more time, then one more 3 power k. And that's how it will get full, right? I mean, this stack will be having 3 power k, or okay, this is having 3 power k plus 1, right? So the next time you put, so it is 3 power k plus 3 power k. Yeah, this is 2 into 3 power k. And the next time you put, it will be 3 into 3 power k, which is 3 power k plus 1, right? The next time you put, it will be 3 into 3 power k. Basically, this is thrice of this. So what I'm trying to make a point is that you need to transfer from here to here all of the elements. It won't be the case you have to transfer some of the elements, right? Is this clear to everyone? It won't be the case that you have to transfer just one element, two element, three element. I mean, you have to transfer all of these elements if you have to transfer. Otherwise, you won't be transferring, right? No, Twinkle, you are getting it wrong. The question is not about the question. I mean, this part A. Part A is not about that what you have done. Okay. I mean, how you have inserted those n elements is not about this. I mean, see, the stack is already having this case. Stack is already having these n elements. Now, how you achieve, how much time complexity you did to this n elements, it's not about this part A. Okay. Part A is saying that if you're pushing one more element, then how much time you can take? See, I agree that initially, let's suppose this is the very first element that might have traveled from here to here, then here to here, then here to here. It must have traveled multiple times, right? This must have traveled multiple times. This must have traveled multiple times. But that's not the question. I mean, you are right in the statement, but this is not the answer of the question. Question is asking something else. Question is saying that worst case running time to push one more element, okay, onto the multi stack containing already n elements. How you have got these n elements, it is not the case in the question. We can analyze this, and we will be analyzing this. That's not the problem. But the thing here is that they are not asking this. They are not saying that how many times this has moved out these things, right? They are saying this is already there. In how much time complexity you got this scenario, is one other question that we can answer and we will be answering. But let's just answer one other question, which is that this stack configuration is already there. Now you are pushing one more element. Then how much time you will be taking? Okay. Is this fine to everyone? Okay. So yeah. So last n insertion time, you can ignore all how much time total you are taking. You don't need to count it. You just need to count that. Okay. All of this is full. Now just insert one more. How much time this is taking? Only this. Okay. Only this. Is it that we start moving, starting from rightmost to leftmost full stack? Rightmost to leftmost. I'm not getting. This is the rightmost, right? We never transfer from rightmost to leftmost. Okay. So basically they are asking, is this clear to everyone? That how you are getting, like the question is that you are having this scenario. Okay. You are having this scenario, which means you are already having n elements. Now they are asking, what is the time to push one more element? Now to push this element, what you will be doing? You, in the worst case, you may be transferring all of these elements. So tell me how much time this all of these elements will take. Every element will be taking order of one time. Will it be taking more than order of one time? That is my question. Every element will be taking just order of one time, right? Similarly, you need to transfer all of this here. And since it is thrice of this, so definitely once it is empty, it can hold this, right? Similarly, you need to transfer all of this here. So all of these elements are just taking order of one, I mean, individually. So if you need to transfer this, then you will be taking order of n time. Just to transfer this element, because you have to transfer all the elements, right? How you have got this scenario is just different question. Is this okay to everyone? Okay. Now let's just answer this question. Okay. That how much time we are taking. So the question which we can pose is basically a different question, which is that what will the total time to push n elements? This is more interesting question. That if you're pushing n elements, then how much time you're taking in total to push n elements? Now you will be thinking about this, that okay, this element might have jumped from here to here and then here to here. Now we will be thinking about this case in the part B. Okay, we will be thinking about this case in the part B, but not in the part A. Is this clear to everyone? In the part A, they are saying that already it is containing n elements, you just push one more. Okay. Okay. Now let's just see that how much total time we are taking to push n elements, not just nth element. Okay. Yeah, that is interesting, right? First element will take just constant time. But when you're pushing the next element, right? So the next element, you need to push it here, and then you will be pushing the next element here. It will take order of two, I mean, two time, because you need to pop it from here to here, push it there, right? Yeah, nth element is taking n order of n. Okay, I mean the last insertion is taking order of n, but it might be the case that, I mean, you need to add how much the first insertion is taking, how much the second insertion is taking, how much the third insertion is taking, right? Like that. You need to add all of this. This is taking order of n, but they may be taking just one, maybe. Then ultimately it is just order of n. I mean, what you are saying that n, right? What you are saying that everyone is taking n. In that case, it is right. I mean, it's not wrong. But the thing is that order of n square is right, but it is just over approximation. It might be the over approximation. That's the thing, right? It might be the over approximation. I mean, that's not wrong. So we just want to analyze the things carefully. See, order of n square is not a wrong answer. if someone says that order of n square has the is the total time to push n elements, I will happily accept it. But this is not the tightest. Maybe, I mean, I'm not saying that if we do it, I mean, I just want to do the more careful analysis. I'm not saying that order of n square cannot be the tightest. Let me do the more careful analysis and let's just see if we are still coming up with the order of n. Maybe the ultimate answer is order of n, right? Have you understood what I'm saying? So basically, I'm saying everyone is taking n, and then order of n square is the correct answer, which might be the over approximation because I have not done the careful analysis. Let me do the careful analysis. Maybe I will again end up with the order of n square. Okay, let's just see if we can do some careful analysis. Order of n square is correct, but might not be the tightest. Is order of n cube correct? Tell me. Is this correct? This is also correct, but might not be the tightest, right? Similarly, out of n power 4 is also correct, but might not be the tightest. So let's just see. Let's just do some more careful analysis, right? Okay. So first element, I mean, if we think in that terms, that first element will be taking order of 1. Then second element के लिए ये shift करना पड़ेगा. Third element, okay, something like that. Let's just think in that terms that if we want to push, let's suppose n elements, I mean a total n elements, then after the n elements, how does this multi-stack look like? Okay, let me just see this. So let's suppose this is the first stack. This is the second stack, the third stack, the fourth stack, something like that, right? The fifth stack and so on. Let's suppose after n insertions, k stacks are full. Okay, k stacks are full. After n insertions, okay, so which means let's suppose from S0 k plus 1 or k doesn't matter. From S0 to Sk, these stacks are having at least one element. Okay, so my claim is that, I mean, not the claim, but one I can say one thing that I'm assuming that, I mean, there may be some finite number k, right? So there has to be some stacks which are full. Sorry, which are having at least one element. So after n insertions, let's say S0, S1 till Sk are having at least one element. Is this okay to everyone? I mean, कोई तो k होगा ना. There might be some k. There must be some finite k. जहां तक ये full होगा, after that everyone is empty, right? Let's suppose this is Sk are having at least one element. Is this okay to everyone? Tell me. Just think about it. I mean, I just assume that there is some k. I don't know the k. Maybe k is n. Maybe k is n by 2. Can k be the greater than n? Can k be the greater than n? Can there will be 2n stacks which are full just because of the 2n stack which are having at least one element just because of the n elements? I don't think, right? Which principle tell you this from discrete math? Can anyone tell me? I think pigeonhole, right? You might apply the pigeonhole principle. So that tells that this, I mean, if everyone is having at least one, so there cannot be obviously more than n. So basically, obviously, this k must be less than n or less than equal to or whatever. So basically, I mean, k cannot be greater than n, right? K less than equal to n. That is I'm sure of. But let's not worry about it. The value of k. Okay, I'm not worrying about the value of k. I'm just saying that there are some k stacks which are full. Sorry, not full. Don't pay attention on this full word. So basically, there are k stacks which are having at least one element. Okay. Is this statement okay to everyone, or there is some problem with this statement? Can I write this kind of a statement? I think we can definitely write, right? I'm not claiming the value of k. We can claim. I mean, we will see that we can claim or not. But at least till now, I'm just saying that okay, there are S0 to Sk which are having at least one element. Okay, tell me the minimum number of elements this Sk can have. Can you tell me the minimum elements this Sk can have? This is very interesting. What are the minimum elements that Sk can have? So Rishesh is saying 3 power k minus 1 or something. I'm asking minimum. Just tell me the minimum elements that this any SI, okay, any stack SI can have. The minimum number of elements. Maximum could be full, obviously maximum could be full, but tell me the minimum elements. Can it have just one element? This Sk, can it have just one element? It means you cannot obviously directly push here. You must have transferred from here to here. This one element you must have transferred from here to here. Do you transfer one element according to the algorithm? Do you ever transfer one element? You transfer only when all this stack is full, isn't it? You transfer only when this stack is full, right? So you must not have transferred this one element. So there is no chance that you can have just one element here. Just think about it. See, the only way that you can have one element is basically you must have transferred this element from here to here. But you cannot transfer just one element because that's not the algorithm is saying. That's not the procedure is. So now tell me the minimum number of elements this Sk can have. It cannot have one element. Minimum, it cannot have one element. At least one I'm assuming. Okay, just assume that at least one. I mean, कुछ element है इसमें. Let's just assume. Let's not say it is 0. I mean, let's not worry about the empty. Yeah, Twinkle is saying that we cannot access this Sk without filling this Sk minus 1. Yeah, that is true. But all of these elements, what you're doing, you're summing up all of these elements and then you're saying that this is the element that is here, right? No, all of these elements we are not putting. See, this Sk can have any element only when you are transferring from here to here. Just after one transfer, how many elements this Sk can have? Just after one transfer. 3 power k minus 1, right? I mean, this is Sk minus 1. This is having 3 power k minus 1 or something. So basically, the minimum elements can be only after one transfer. It cannot be one. It can be after one transfer. मतलब ये पूरा की पूरा इसमें जाएगा. ऐसा it cannot have just one or two elements. That's what I was trying to make a point. It can only have 3 power k minus 1. Minimum elements this Sk can have. Is this okay to everyone? Maximum obviously 3 power k. Maximum obviously 3 power k, minimum 3 power k minus 1. Okay. So I hope this is very much clear. Let me just write it here. That minimum elements this can have is 3 power k minus 1 and maximum it can have is 3 power k. Okay. I mean, I'm assuming that these are the non-empty. I mean, minimum, just don't assume 0 because I just said that everyone is having at least one. Okay. At least one I'm assuming. So don't worry about the 0 case. I mean, I'm saying that, okay, at least one everyone is having. So this stack can have minimum elements here. In any stack actually is 3 power k minus 1. Maximum elements here could be 3 power k. Let me know if this is fine to everyone. Minimum, you cannot have less than 3 power k minus 1. Maximum, obviously, you cannot have more than 3 power k. Because this is the size of the stack. Right? Okay. So, now let's just talk about this n. Now can we talk about the relationship between n and k? See, n is the total number of elements, right? अगर सब में मिनिमम भी होंगे, ओके, सब में मिनिमम भी होंगे तो इसमें एक है, इसमें भी आई थिंक 3 power k minus 1 समथिंग लाइक दैट, राइट? सो सब में मिनिमम भी होंगे then maybe actually this minimum maximum is just differing by the constant, to be honest. मतलब जो भी minimum की series बनेगी ना, I mean 3 power k minus 1 तक बनाओ, मैक्सिमम की सीरीज ये बनेगी, राइट? मतलब मैक्सिमम मिनिमम में देयर इज नो डिफरेंस. आई मीन टोटल एलिमेंट्स में 3 का मल्टीप्लिकेशन होगा. आई मीन दैट्स जस्ट अ वन सीरीज, राइट? सो बेसिकली इफ यू काउंट द मिनिमम, लाइक आई एम नॉट वरिंग अबाउट 3 power 0 1, like little bit constant you can adjust here and there, but this is basically asymptotically you can say this 3 power k minus 1, right? And maximum also like some in 3 power k. So basically even if you sum this up, what will the answer? So what is the summation series formula? A r plus ar square. What is this? Ar power n. Ar power n plus 1. I don't remember exactly. R power n something like that, right? Sorry, I don't remember it exactly. But anyway, this will be in 3 power. I mean, asymptotically, let me just talk asymptotically. It will be 3 power k, I think, right? Something like that, right? So basically, it will be 3 power k. Okay, this is the formula, which is a into r power n minus 1 upon r minus 1, right? Yeah, that's the formula. So 3 power 0 1 into r is 3, right? R is 3 power n is the number of element minus 1 upon 2, some 3 power k minus 1 upon 2, something like that, right? Okay, so basically it will be, I mean, it will like this n, I mean minimum. So this n, you will say that n will be at least this much, right? So you will say that n is at least this much, and maximum n could be this, right? 3 into this, just the 3 into this, right? I mean minimum this much and maximum this much. Is this okay to everyone? Just a 3 into this. I mean, you can multiply 3 in this series, because minimum and maximum both are differing by just 3. I mean, the series will differ just by multiplication of 3, minimum and maximum. So basically, I mean, that's where the theta, if you recall the formal definition of theta, right? I mean, this is basically asymptotically, this is in between the theta only. For some constant, this is theta power k into some constant C1. And I don't want to go into that complexity, but still you can understand that this n is just theta power k. Sorry, theta into theta of 3 power k, right? I mean, that's in theta. So basically, you can just ignore all of these constants. You can say n is just theta power k. Is this okay to everyone? So basically, you can say k is log n. Okay, I mean, it is just a some constant multiplication of log n. Let me know if you have understood this. नहीं आया समझ? See what I'm saying that you are having minimum these elements, and see n is one number which is fixed, which means n is at least as large as this, and at most it can go this. So at least as large as this, because this n is fixed. You cannot change this n. This is the fixed number. Okay, n is the number of elements that you are having in the stack. Okay, see, n is the total number of elements that you are having in this stack. The total elements is n. Now I'm just trying to find out the relationship between n and k. Okay, so I'm saying the minimum elements that you can have, that this n is at least as large as 3 power k minus 1 upon 2, or at most it can be 3 into this, right? Okay, so Siri is asking, sir, why is that we are assuming the case where we have the minimum elements in k stacks and not storing all the stacks being empty? What is your question? We have minimum elements in k stacks. No, I'm not assuming any minimum or maximum. See what I'm saying. Let's just go step by step. Very simple. I'm saying, let's suppose after n insertions, I'm saying some k stacks are filled. Okay, some k stacks are having at least one element. This is my one statement that I made. And every one of you agreed that that is correct. I mean, obviously there might be some k. We will figure out that what is the relationship between k and n. But yeah, I'm saying that obviously, like you have to stop somewhere, right? I mean, you cannot. That has to be contiguously first of all, and then you cannot stop at infinity. I mean, since n is a finite number, however large it is, but there might be some there must be some fixed k. You will be saying that okay, till S0 to Sk, let's suppose there are some stacks which are having at least one element. Okay. Now, since everyone will be having at least one element, so now I'm trying to find out the minimum and maximum relationship, right? Okay. So why not starting with all stacks being empty? Yeah, you can do that. You can do that. No, no. You can do that kind of analysis, but that might be some other way to analyze. Okay, what I'm saying is that I'm just see, we will be starting with a stack being empty. That is okay. We have not even started pushing. Okay, let's suppose we have not even started pushing. Okay, we are just saying if we push all the elements, suppose if we push all the elements after n insertions, suppose k stacks are full, then this sk cannot exceed this log n. Okay, that's what we are saying. Okay, so basically whatever the elements here, we basically, I mean, this sk won't exceed this, k won't exceed this log n, so something like that, that we just try to make a conclusion, right? Okay, so now let's just now do the question, which is saying, okay, so let's just do the question from very beginning, which is saying that find out what is the time complexity to insert n elements, right? This is the question. Okay, so let's suppose you push one element. Okay, then you push two elements, then you push third element, and like that, so on and so forth, and then elements are jumping forward, jumping, and at the last, let's suppose that at last they can jump to sk. Okay, there must be some finite k. So basically the first element that you have pushed here might have jumped from here to here, might have again jumped from here to here, might have again jumped from here to here, and might have again jumped from here to here, and finally the first element that you pushed at the very beginning, that might be at here, right? Is this okay to everyone? So the first element has made how many jumps? Exactly k jumps or something, k plus 1, k minus 1. I mean, let's not worry about it. Okay, so k jumps first element has made exactly k jumps, right? Is this okay to everyone? Why that is the case? Because I'm strongly saying that at like this k is some number. Let's not worry about what is this exact number, log n, n square n, or let's not worry about it. But I'm making one claim is that all of this stack, I mean, are having at least one element. Okay, so basically one element is basically jumping from here to here. So the first element had made k jumps. In the total process, the first element has made k jumps, right? The second element, which is, let's suppose, here only in this stack. See, whatever the elements here in this stack, if this is having, let's suppose, x number of elements, then those x elements have made how many jumps? K jumps, right? I mean, यहाँ पे आने के लिए k jumps करने ही पड़ेंगे, कोई, there is no other way, कोई तरीका ही नहीं है ना. You're getting my point? So basically, however number, see, I'm saying the first element is having the k jumps. Similarly, let's suppose the second element is also here, then it must have made the k jumps, right? So minimum, okay, I mean, you can say again, is actually this won't matter, but let's just have this. So let's say that this is 3 power k elements. Okay, I mean, this could be 3 power k minus 1, k plus 1. Actually वो 3 का ही difference है, कुछ multiplication 3 का difference है, कुछ बड़ा difference नहीं आएगा. But let's say 3 power k elements. Okay, these 3 power k elements are here, and how many jumps they have made? K jumps, isn't it? K jumps. Similarly, these k minus 1 3 power k minus 1 elements here, someone will claim that, okay, this is not 3 power k minus 1, this could be 3 power k minus 2. Yeah, I agree. Okay, don't worry, I'm taking the 3 power k minus 1 just to make the calculation simpler. Just multiplication of 3, that's the only difference. Okay, basically this 3 power k minus 1 elements must have made k minus 1 jumps. Is this clear to everyone? यहाँ पे जितने भी एलिमेंट्स हैं उनको they must have taken 3 power k jumps. And how many elements could be there? Maximum 3 power k, minimum 3 power k minus 1. Okay, let's not worry about it. Let's take it 3 power k. So basically 3 power k elements must have made k jumps. 3 power k minus 1 elements must have made k minus 1 jumps. 3 power k minus 2 elements must have made k minus 2 jumps, right? So basically it depends on the stack, in which stack I'm here. Okay, so basically after n insertions, okay, इनमें कुछ elements हैं, whatever the elements, let's not worry about it. But what I'm saying, k into 3 power k and k equal to 0 to some number. And what is the number that k can go to? This is also interesting. So k can go to log n, right? log n, because k can never go beyond log n. Yeah, base 3. Yes. Okay. So that's what we have derived. I know it is very complex, but I hope I'm making a point here. Are you understanding what I'm trying to make a point? So basically, these all elements must have made k jumps. That's why I'm having this. These all elements must have made k minus 1 jumps. That's why I'm having this. Similarly, these all elements must have made k minus 2 jumps. So k minus 2 into 3 power k minus 2, like that, right? So basically, we need to add all of this. We need to add all of this. So k into 3 power k, and here, or you can say I into 3 power I, right? Maybe if this is confusing, I don't know if I will be, I think, more confusing, but okay. Right. So 0 into 3 power 0, ultimately k into 3 power k. And k value we know, which we will be putting at the last, which is log n, right? Log base 3 or something like that, right? Is this formulation is clear to everyone? This is the total time we are taking to push n elements. And what is the relationship between k and n? We will see this. I mean, we have already seen this, but we will put it later. So this is the time complexity. This time complexity, if you calculate, this is AGP. Okay, this is the AGP we will be calculating, but that will be in the terms of k. Let's suppose this is 3 power k or something. Okay, I don't know, but I don't know. Okay, 3 power 2 k or something. Let's suppose जो भी इसका final answer आएगा, that will be in the terms of k. And then you have to put the value of k to finally get the answer in it. Is this okay? Okay, great. So I'm not sure if everyone is convinced, but you can just try to convince yourself. Is that यहाँ पे जितने भी elements हैं that have taken k jumps, number of elements here must have taken k minus 1 jumps, and how many elements could be there? That's also one interesting question that we have answered, which is 3 power k or 3 power k minus 1. I mean, it is just a matter of 3. Okay, so let's just solve this series and let's just find out the answer in terms of k, and then we will be finally putting the value of k, right? Sorry, I into 3 power I. So I think that was too complex question. Maybe I might not have put it, but I think for the practice it is okay, right? Okay. Yeah. So can you solve this AGP? Asymptotically, just tell me the answer. You don't need to solve. Okay. Let's suppose this is S 2 into 3 square plus 3 into 3 cube plus K into. I think you need to multiply by 3. Okay. We have already seen this in the fundamental lectures, right? So if you multiply by 3, this is 1 into 3 square, 2 into 3 cube, and this is, let's suppose, k minus 1 into 3 power k minus 1. So it will be k into 3 power, sorry, k minus 1 into 3 power k plus, and ultimately it will be k into 3 power k plus 1. Yeah. Okay. Now what you can do, you can subtract one from another. Maybe you can subtract. Okay, this is 3s. So what you should do, maybe you can subtract this from this. This is 2s and minus 3 minus or maybe you can subtract like this in the normal way, right? This is minus 2s. This will be 3 plus 3 square plus 3 power 3 cube, and then it will be 3 power k, and then ultimately it will be minus of k into 3 power k plus 1, right? Okay, this is 3 power k. So asymptotically, you can say this is just 3 power k. So this is 3 power k minus of k into 3 power k plus 1, which is minus 2s. What is that 3 to 3 power k? So maybe I can do it more carefully. Okay, so this term is coming out to minus 2s equal to, I think this is the formula that we have applied. a into r power n minus 1, I think 3 power k plus 1 minus 1 by 2, right? Something like that. Minus k into 3 power k plus 1. Then it is s equal to k into 3 power k plus 1. Minus 1 plus 1 doesn't matter. So it will be k minus 1 into something like that, right? Okay. So finally it is k minus 1 into 3 power. I mean, minus 1 plus 1 actually won't matter much. So maybe you can ignore this plus 1 because this is 3 into something, right? So 3 power k into k minus 1. And then k into 3 power k minus 3 power k. So you can again ignore this. So it is finally in the terms of k into 3 power k. I mean, asymptotically, okay? So k into 3 power k. Now, k is log n. So basically, the ultimately this series which I wanted to compute, I into 3 power I, which is I equal to 0 to k, is coming out to be asymptotically, it is basically k into 3 power k, right? And then ultimately this k is log n. So this is log n into 3 power log, it was log base 3. So basically it is n log n. Right? So basically to push n elements, you are getting total time to push n elements. We are getting n log n, right? And what we over approximated, n square. We were saying that n square se zyada nahi ho sakta. That was also true. I mean, you were saying earlier order of n square, which is less than or equal to n square. That was also true. But this is better calculation. I mean, this is just a little or maybe more careful calculation, you can say, right? And what was the worst case time complexity? Just to push one element. Just to push one element, it was theta of n. Okay. To push n elements, it is n log n, theta of n log n. To push n elements. Okay. It is not the case that every element is basically having the order of n. That's the thing. Basically, most of the can element tell me most of the cost is incurred by which elements? The elements which are in this stack, right? The elements are which in this stack is basically have jumped too much, which means the initial elements have done most of the work. Then the work is reducing by the factor of 3. Then the work is reducing. Then the work is reducing. Then the work is reducing, right? Something like that. So basically, total work you have made to push n elements is n log n, and worst case n. Okay, so that's why you can say that final answer is n log n here, and this is order of n, or maybe you can say theta of n, and this is theta of n log n. Okay. Okay, so I hope this is enough for this question. Let's just move to the next question, right? Okay, so don't worry. Like I mean, this was I can say quite hard question. So if you were not able to solve, that is completely fine. Okay. Now I think you can do this question, right? So just check the answer. What is the answer that you are getting? Can anyone tell me the answer? Rear of the queue is the head of the list. What is the possible worst case running time for the NQ and DQ? Okay, order of n for the NQ and order of 1 for the DQ. So basically they are saying, suppose you implement a queue using a singly linked list with head and tail pointers such that front of the queue is the tail of the list. Okay, so basically they are saying the tail of the list is front. Front means you DQ at the front or you NQ at the front? Tell me. This is the front. So I think you will be DQing at the front, right? So you DQ from here. DQ. And the rear of the queue is at the head of the list. So you NQ here. So NQ won't be taking yeah, so I think the answer should be B, right? In that case. Yeah. So answer should be B in that case. Okay. So NQ will be taking order of 1 and DQ will be taking order of n. Why DQ is taking order of n? Because if you want to delete this, you have to set this pointer. Since it is a singly linked list, so you have to set this pointer to be null. And can you set this pointer to be null by just pointing here? No, right? You have to traverse till this point. So that's why order of n for the DQ. Now, some people argue, like, have you seen that argument that you just swap these two elements and then you need to basically just delete this or something like this? Have you seen that argument? No, that is not rubbish, but there is a catch in that argument. So basically, the argument is that, which is very popular argument, and that is popular in case of um, like competitive coding, you can say. Suppose you are pointing here. Let's suppose this is 1, this is 2, this is 3, this is 4, this is 5. Suppose you are pointing here and you want to delete this. Okay. Now, some people say that what you can do, let me think about it. What they say, I think that won't be applicable for the last. Yeah, that could be applicable for the second last. But how you will be swapping 4 and 5, right? Moving at the head at first. You want to delete this 5. So, okay. Maybe you can swap this 1 and 5 because you have both of these pointers. So, then what's the benefit of, I mean, if I do this, I need to set this 4 to be null, right? And you cannot set this 4. Okay, let's not worry about it. Basically, yeah, obviously you cannot change the order of elements. So basically, in general, I was saying that let's suppose that you are having this thing. Okay, let's suppose this is not the last element. Let's suppose in general I want to make 1 point. Let's suppose this is 6. Suppose you are pointing here. Can you delete this? Can you delete this 5? By just pointing here, you have to set this 4 to be 6, right? I mean, after deletion, you should be looking like this. It should be looking like this. Right? Okay. Can you delete this 5 if you have just pointed to this? See, can you change this pointer to 4? Can you change this pointer to 4? So basically, some people argue in one way. They say that what you can do, you just swap this 5 and 6. Basically, you have pointed to both. You can definitely swap this 5 and 6, right? So if you swap this 5 and 6, this will be 6, this will be 5. Now you have pointed to this, then you can definitely delete this 5. Now you delete this 5. Why? Because you can definitely ask this 6 to point here 7. And then you can definitely say that 4 is pointing to 6 and 6 is pointing to 7. Understood my argument? So the argument is that you want to delete this 5. Ultimately, you want to achieve this, right? What you do, the first step is this, swap these two, right? Swap these two. This will be 6, this will be 5. Now you delete this 5 because you can definitely set this to 7, right? Now you can delete this 5. Now once you swap, you can delete this 5. Is this okay to everyone? I mean, there is no flaw. Don't worry about the, don't look for the fault here. This is fine. This is fine. Okay. Let me know if everyone has understood this. You can swap this. You can delete the 5 later. Okay. I mean, instead of deleting the very right, this node, you can just ask this swap and then you can do it. Okay. This is one thing. So basically, if I just say that if it is not a last element, okay, if I just say worst case time complexity to delete a middle element, I mean, if you're pointing to any random element, then what could be the worst case? You will say just order of 1. Why this logic, right? The logic I have just shown you, it is basically just doing order of 1 operation. Let me know if this is fine to everyone. After swap, 6 is not pointing to 7. No, you can definitely ask the 6 to point to 7, right? I mean, you can definitely change this pointer because you have the pointer to this. Your pointer is pointing here. That is not an issue. You can definitely ask this 6 to point to 7. So basically, this is the order of 1 operation that you can do. But there is a catch. if the statement is like that, that there is a linked list, okay, if the exact this statement is there, if there is a linked list, in that a pointer is pointing to some middle node, if you want to delete that middle node, then what is the worst case time complexity? Can anyone tell me? It is seeming to be order of one, right? But there is a catch here. Can anyone think about the catch? The catch is that it is little tricky to think that here this linked list may not be having integers. Who told you that linked list is having integers? Which means, who told you that this swap is taking order of one? This linked list in general may be having a big file. I mean, there could be in operating system, you will see there could be the big memory here, and at the end of memory, you will be having one small pointer. Okay, that is called linked allocation. In the linked list, in the operating system, you will see basically the data here could not be integer itself, right? Data is too much that if you swap it, you will be taking 4 hours. I mean, you don't know the time complexity to swap. You cannot assume that swap is taking order of one. That is the thing. Yes, if it is integer, it is taking order of one. What if it is not integer? Suppose there is a big file, or there's a big memory that you will see there in the operating system, that is called linked allocation. Okay, there that is actually the practical case. Okay, so here at the end of this chunk of memory, we store one pointer that points to somewhere again in the chunk of memory. Okay, and then this also points to somewhere again in the chunk of memory. So basically that's how we form our linked list. Suppose now if someone asks you to delete this, then can you swap this chunk of memory and this chunk of memory? Can you swap this? I mean, is this just order of an operation? Can you swap can you put all of this data here and all of this data here? No, right? So basically in general, linked list may not be having even integers. So the swap is a catch here. The swap is not order of one. That we were assuming. Okay, is this clear to everyone? That the swap itself may not be order of one. Okay, cool. So basically, don't just assume that swap is taking order of one. That is my case. And even you don't know that how much swap will be taking, because it is basically not given to you that what is the size of the data, right? That each linked list is carrying. Okay. So let's not worry about it. But I was just saying that the common mistake is that we assume that swap is order of one. Okay. If swap is order of one, then you can do it. Anyway, let's not worry about it. Okay. Were you able to solve this question? Yeah. So basically, you have one stack. You are pushing it. If that is the case, you are popping it. If that is the case, then you are pushing it. Then you are popping it. Then you are pushing it, popping it. Then this square bracket, then cancel out. Then this. Is this 2 or 3? Okay, I'm just getting 2. Maybe I did some mistake. This, then you push this, then you pop this, right? Okay, this 3 is done. You push this, you pop this, you push this, you push. Okay, you push 2. Okay, now you push this more, right? So yeah, so now you're popping. Okay, now these 3 are pop. So or this will be taking 3, right? Okay. Now let's just solve this question. What they are saying: Alice has 2Q. Okay. Okay, let's just I mean, I will be coming to this question in a while. Let me see any other complex question. So is this question okay to everyone? So what they're saying, they are putting all the elements from, I think, Q to stack, right? And then stack to something like that. So I think we saw this, right? I think it will be reverse. Is it reverse? Is the answer C? Can anyone tell me? Okay. Okay, I'm trusting you. Basically, we have seen this, right? I mean, if you do stack and queue, I mean, you do this and then you do this, then the answer is reverse, right? So we have seen this, right? Okay, let's just solve this 24 and 25 first, and then I will come back to that question. Okay, that I have just skipped. So a stack of integer implemented using an array. So they are saying that this is one stack. Fill up the missing code, push, pop, and top. Okay. So push is this, and ignore underflow and overflow in stack. You can assume the underflow and overflow handle before calling push and pop. Okay. So basically, they have not given that. Okay. The top is initially what, right? Below the machine code in the push and pop. Okay. So for the push, they are saying, is this correct that you can do as of data? Okay. So in this data, this is one array. So in this array, you need to push, right? Okay. So basically, in this array, you are first, wherever, let's suppose this top is pointing to the filled element, right? You will be first incrementing. So as of top will be pre-incremented. You're putting the data, right? I think that is fine, right? So this should be the push operation. So basically, they are saying you increment this top, you put the data, and underflow, overflow, let's not worry about it, right? Similarly, here they are saying that so basically this is having a more priority than this minus minus, because you go from left to right, right? So they are saying go to the top, and then if you want to pop it out, then just decrement it, right? Go to the top and just decrement it. Okay. Yeah, that is fine. I think that can be the pop. And here they're saying that if you just want to look at the top, then you can just look at the top like this. So A, B, C are the correct answer, right? Okay. And I hope this 25 is also easy. You might have done it, right? What is the answer? Okay, they are showing the push and okay, you can solve it, right? Cool. Now let's just go to this question. So what they're saying is that, let me just explain you the question. There are two Q and R, right? There are two Qs, Q and R. Now this Q is basically having, I mean, these are the two Qs, and there are basically 100 integers, 15 even integers, and sorry, 50 even integers and 50 odd integers. Now there is a person whose name is Alice. So this Alice wants to put these all integers into this queue. Okay, which means like, what are the options? Let's suppose this is one queue, this is one queue. If you want to put this 100 integers into the queue, maybe what is the one option? You can put these 50 even here, 50 odd here, right? So basically you can put 50 even here, 50 odd here. That is the one option. Another option could be, maybe you can put 25 even here, right? 25 even here, 25 odd here. Similarly, 25 even here, 25 odd here, right? Similarly, there could be many other options. 25 even here and 25 odd here. Okay. What could be some other option? Maybe you can put 10 even here and 25 odd here, 15 even here, right? Something like that. I mean, just 10. It is not necessary you have to put 50-50. Okay. I mean, you can just put 10 even here and remaining all the elements here. Sorry, what is the remaining? 50 odd is remaining, and 40 even is remaining. Yeah, that is correct. Okay, 50 odd is remaining, 40 even is remaining. Yeah, you can put all 100 in one cube. So there are many options, right? I hope you understood. So basically, Alice, one size if q is if 50 only. No, q size is not given. It is not necessary that you have to put only 50 or something. Okay, so q is, let's suppose that it is capable to hold more than 100 integers. So basically, there are a couple of options. That's what this question is saying. So now they're saying that you do. I mean, this Alice can do in whatever way it wants to put. Okay, there are many possible ways. Now there is another person, which is Bob. Bob will do one thing. It does two things. Step one, pick a queue at random Step 2, pick a number from that queue. Suppose it has taken this queue, okay? Now it will be picking a number, randomly a number from this queue. So basically you cannot directly pick a random number. So basically, I mean, you need to, if you, let's suppose you need to put this number, you need to pick this number. So what you will be doing? You need to pop all this number out and maybe you need to push it again. I mean, that's called round robin. Okay. That's the round robin scheduler, but that's fine. But in layman terms, you can understand that pick a queue at random, then pick a number from that queue at random. Okay. So basically what is happening that you have Alice and Bob, and Alice is basically distributing in any way she can distribute, and Bob has to pick one queue, and then from that queue that Bob will be picking one number, right? So that's the scenario. Now suppose that whatever the number Bob is picking, suppose that number is even or odd. If the last number to be processed, if that number is odd, then Bob will win. If that number is even, then Alice will win. Okay. So basically these are the two queue. Let's assume that in these two queue, numbers are distributed in such a way that 50 even here, 50 odd here. Okay. Now tell me, what is the probability that Alice will win? What is the probability? Let's just calculate this probability. What Bob will do? Bob will be picking. See, Alice will win whenever. Okay, you can say with. Okay, can anyone tell me what is the probability that Alice will win? This is quite easy question here. In this particular case, if 50 even 50 odd, Alice will win if Bob picks even number. Yeah, 1/2 is the probability. Yes, that's correct. Because if Bob picks this Q, that is the half probability of picking this Q and half probability of picking this R. If Bob picks this Q, then what is the probability that Alice will win? I mean, Bob will picking even integers, 1 probability, right? If Bob picks this R, then what is the probability that Bob will picking the even integer? 0 probability. So basically, 1/2 is the probability final, which is basically, I mean, picking the probability of picking this Q, right? Here with the 1/2 probability, Alice will win. Okay, cool. So basically, this is one case where Alice will be winning with 1/2 probability. Let's just check if we can increase this probability. Okay, suppose instead of this 50 even 50 odd, let's suppose some even I'm putting here and some odd I'm putting here. So suppose I say see what is happening here. Just one thing, I just one thing that got clicked in my mind is that, I mean, here this Alice is winning because this Bob is picking this Q, right? Alice is winning because this 50. Tell me, because of this 50, Alice is winning. If this is just one even integer, okay, if this is Q is having just one even integer and 99 others are here, then tell me, then also after picking this Q, Alice will definitely be winning, right? If it is even 2 integers, then also after picking this Q, Alice will definitely be winning. You're getting my point? So basically, even if there is no odd integer, if there is 0 odd integers, then Alice will definitely be picking, if Bob picks this Q, 0 odd integers, and at least one even integer, obviously, right? Then Alice will definitely be winning. Okay, is this okay to everyone? So basically this 50, what I'm trying to make a point is that this 50 is too much to waste. We are wasting 50 in integers, I think, right? Even if it is just 1, then also I can make it 1. Then also this is 1/2. I mean, this is too much we are wasting here. Okay, so basically this 50 is too much to waste. I mean, we will just analyze, but just one intuition that just came into my mind is that if we transfer some of this 50 here, Okay, if we transfer some of this 50 here, then what will we be doing? Are we okay? We are not transferring anything from here to here. Don't worry, we are not doing this. Okay, we are just transferring from here to here. Let's suppose 40 even. Okay, 40 even, and 50 odd definitely, and 10 even is here. Then tell me what is the probability that Alice is winning? See, 1 by 2, I'm not decreasing this probability. With 1 by 2 probability, Alice will definitely be winning if it chooses the Q, right? If this chooses the Q, or Alice may choose the R with 1 by 2 probability. If it chooses the R, then what is the probability that Alice will be winning? Which means what is the probability it is picking this even integer, which is 10 by 60. Is this okay to everyone? So these are the 10 and out of 60, right? So what is happening here is that ये 1 by 2 into 1 तो मैंने preserve रखा. I increased something here, right? I increased something here from 0 to I increased 60, 10 by 60 or something like that, right? कुछ improvement मैंने कर लिया. I made some improvement and finally it must be greater than 1 by 2. So are you getting that how we are improving the things? Right? Here, this 50 is too much to waste. Similarly, can you improve again? Can you improve again? Can you improve again? How? What is the best improvement in this case that you can make? I mean, which in this case means you are only allowed to put from here to here. Let's just make it. Just a simple analysis for now, which means I'm not putting any odd here. What is the minimum even integers that I need to put here such that I get the best possible probability? What are the minimum even integers? See, अगर 50 से कुछ मैंने 10 इधर दे दिए, 10 इधर दे दिए, I am increasing, right? If I'm giving more integers, more even integers from here to here, let's suppose I just keep 1 here. Okay, I just keep 1 here, 1 even integer here. Okay, 49 even integers I'm giving to this. Then also I'm definitely winning. And here it is 49 upon 99, right? So you can calculate it will be greater than this 1 upon 6, right? So I mean you are basically, I mean obviously you're putting the more elements here, so the probability of finding the even integer will definitely be increasing, right? I mean you can think intuitively, you don't need to think in terms of the calculation that whether 10 upon 60 is greater or 49 upon 99 is greater. You just think intuitively that here if you pick the even integers in this group, if you pick even integers, it is the more probable that you will pick even integers, or in this group it is the more probable you will be getting the even integers. Obviously in this group, right? In this group. So basically, if you just put 1 even integer here, then I'm making sure that, okay, it is definitely winning. I mean, 50 was too much to waste. So why we are wasting too much, right? Is this okay to everyone? Okay. Now, let's just see if from this case, which seeming to be the best case, but let's just see if we can improve furthermore. Suppose if we try to shift some of the odd integers, see, even integers, there is no point in shifting, right? That's what we have seen. Even integers there is no point in shifting. But suppose we try to shift odd integers from here to here. Okay. Even integers, keep it 49. Suppose you try to move this integer from here to here. This is my question. Is this understood to everyone that what we are doing? So 1 even, 50 odd, 49 even. So what I'm saying, this combination, let's keep it as it is. Okay. Now what I'm saying that can I shift some more integers from here to here and can I still improve the probability? क्योंकि मैंने अभी तक 50 को like I have not touched it, right? So let's assume that you are shifting x integers from here to here. X odd integers, right? Just a second. Okay. So what is the probabilities now? Let's just see the probabilities. What are the probabilities? This will be 1 upon 1 plus x. This will be 49 upon 99 minus x. I mean, sum of all of this, right? Is this okay to everyone? Okay. Now we want to find x such that this probability is maximum, isn't it? We want to find x such that this probability is maximum. Is this okay to everyone? Yes. So we need to differentiate it and then equal to 0, then find out the x on which it is maximum. If you do so, I'm not going to do it. If you do so, then, I mean, if you want, I can do it. Do you want me to do it? See, this is 1 by 2, 1 upon 1 minus 1 plus x. Okay. See, just one thing, just listen me here. This is the probability, right? This is the probability if you are moving x elements from here to here, x odd elements. Now we want to maximize this probability, right? I mean, we want to choose such x that maximize this probability. Let's just differentiate it and then let's just do it. Maybe like you can do it later. Maybe if you differentiate with respect to x, right? I mean, you want to choose x such that this probability is maximum, right? If you do this, then you are getting just x equal to 0. You will be getting just x equal to 0. Okay. Which means there is no need to shift any elements from here to here. It is best that you keep it as it is. Okay. So basically, you will be getting, I mean, the final answer will be like this. Here, this x will be 0 because that is what it is maximizing the probability. So basically, it will be 1 and 0 odd here, which is the best case, and then 50 odd here and 49 even here. Okay. So basically, let me just explain you step by step that what we did. We are saying in one of the queue, if you are doing, let's suppose 50 even 50 odd, then there is no point in doing more than one element. I mean, it is just waste of these even integers. So let's just shift all of these even integers there, right? Now we are saying, can you shift all of these odd? I mean, how many of these odd integers we need to shift from here to here? Let's just assume that is x, and then we want to maximize the probability such that this x for the x such that this probability is maximum, right? Then it is turning out that this x is 0, which means there is no need to shift from here to here. Okay, in the gate, obviously you won't be doing that much. Like you won't be differentiating, and then it might not click to your mind. So basically, you just need to think intuitively. That is what is given in the answer. Okay, there is no differentiation or anything. They have just said like, okay, let's suppose 50 or 50 even, let's suppose this kind of thing you did, and then 1 by 2 is the probability, right? Okay, and if you're keeping 1 here, 1 even, 99 other integers here, you're getting this probability. Now let's suppose even if you try to move some odd integers from here to here, okay, or looks good, they are saying, then how about allocating more even integers to the cube? One more even. Okay, so that's what we have seen. Like, I mean, if you even do this two even integers, that won't be useful. That is intuitively even we are saying, right? So basically, whatever other combination that you will be doing, it will be just reducing the probability. The proof actually like cannot be done without, I think, differentiation, but you don't need to do it. I mean, you can just skip this question because it is involving the differentiation and all. Okay, I mean, to prove it, but intuitively you can understand that if you put more integers here, that's what the question is saying. If you put more even integers here, more than one even integers, then you are not doing anything, right? You are not doing anything great. So just put one even integer here, so that if Bob is choosing this queue, then you are certain to win. If Bob is choosing some another cube, then at least you have half chance, right? This is the almost half, right? Almost half. I mean, this is 50 upon 100, almost 50 upon 100. I mean, almost half. So basically, if Bob is choosing another Q, then you're at least having half of the chance to win. You're not losing too much. Okay. So let me try to think. See, this is 1 by 2. You can take this 1 by 2 common. This is 1 plus 49 upon 99, right? Okay. The complete game is in between these two numbers. Basically, I mean, you can say that you can decrease this one. You can decrease this one by somehow. But if you decrease this one and then you need to increase this, I mean, it will automatically get increased if you decrease this one by, let's suppose, yeah, putting some odd integers here. Maybe you can decrease this one. So basically, one is for sure you're getting in this case. I mean, for sure you're winning, and 49 upon 99 is the probability that you are winning here in the second case. Now you are saying is that if you do any other combination, this one will get decreased. But this 49 upon 99 is not getting increased in that proportion. Okay, this is best to keep it 1, and this almost 1 by 2. Okay, almost 1 by 2. I mean, intuitively, maybe you can understand like this. Otherwise, like you can, I mean, in the exam, maybe it will be the MCQ kind of question. So in that case, you can just try a hit and trial method, right? I mean, if let's suppose 1 even, 50 even, then what's going to happen? Otherwise, I think just to prove this, that this is the optimal strategy, then you have to differentiate it. I don't think there is any other way. Okay, cool. So that is the explanation of this question. Just to make sure that you don't get afraid. So don't worry about the few questions that we might be solving here and there. These are just to have that in the practice set, but might not be directly asked in the gate. So, I mean, they may ask, nobody knows, but what I'm saying is that, like, don't get afraid just because of 2-3 questions. Okay. You should be focusing most of the questions that are there in the practice set. And if there are 2-3 questions that you are not able to solve, that is perfectly fine. In GATE, if you want to get top rank, even top 100 rank, you don't need 100 marks, right? I mean, if I compare, okay, last year, I think paper was little easy, but if I compare 2022, then in 2022, if I remember correctly, then even at 65 or 68 marks, people were getting under 100. Here in this year, I think around at 75 marks, people were getting under 100, right? So basically, you need 75 marks to get under 100. You don't need to solve all of the questions. So there will be some questions here and there which will be too tough. If you are not able to solve, then don't worry, because most of the time it won't be able. It will be the case that most of the aspirants won't be able to solve. Okay, if the question is too tough, and this is that type of question. Okay. No, ordering won't be important here. Just even odd is important, because you are basically doing this round robin scheduler random amount of time, right? So ordering won't be much important. Okay. Yeah. The only use of the queue is basically to have this to say that it is a round robin scheduler. I mean, from this queue you can't just pick a random number. You have to basically do one thing. You have to DQ here, you have to NQ, you have to DQ, NQ, DQ, NQ. So if you're doing it random times, which means you're picking a random number here. The only use of queue is this. Okay. So that is all for this particular practice session. I hope you liked some of the questions. Some of the questions you might have hated, but that is fine. Okay. So there will be the cases that you might not like the questions, but that is perfectly fine. Okay. Just focus on the questions that you are able to solve. Because if you are able to solve most of the questions, or if you are at least able to understand most of the questions, then it is fine for the gate. Okay. Cool. So thank you, everyone. Take care. Bye-bye.